Hello everyone, welcome to Rational Science. Today I'm going to be taking you for a tour to the Twilight Zone. Now, actually, it's much worse. See, the Twilight Zone is imaginable. Today I'm going to take you to quantum mechanics, and that's totally unimaginable. You cannot imagine anything, you cannot explain absolutely anything in quantum mechanics, okay? So, it's going to be some trip, okay? How did we get there? How did we come up with quantum mechanics? Well, until the 19th century, the end of the 19th century, I can't say we were doing good, okay, but at least people were trying to figure out what invisible entities are out there, how Mother Nature does her stuff. You know, how does she do light? How does she do the atom, electricity, magnetism? They had these ideas, and they were trying to figure those out. That came to an abrupt stop exactly at the turn of the century. 1900, end of the 1900, really closer to 1901, Max Planck comes up with a quantum. He comes up with this idea that light, energy, as they call it, comes in discrete packets. It doesn't come continuously, you know, like a river flowing. No, it's chopped off. It's clink, 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 little chunks that come in there. And they call those packets photons, or they eventually ended up calling them photons. And that's going to form the basis of what we call quantum mechanics. Quantum refers to quanta, or quantum, you know, meaning a little packet, a little amount of something, okay? Because they were dealing with amounts. They were all mathematical physicists, and they were only trying to describe it mathematically, okay? So they're not, you know, that changed. That's what changed between what they call classical mechanics, meaning rational mechanics, meaning they were trying to explain things with objects that Mother Nature could be using out there. And again, that stopped at the turn of the century, because after that they gave up on that. As Mr. Feynman says, Nobel Prize, Richard Feynman, he says, the physicist, meaning the mathematical physicists, they've given up on that. I'm trying to understand all that stuff. I'm trying to explain it in rational terms. They've given up on that a long time ago. So, you know, when people ask questions, they ask questions like, you know, how does this work? What is the mechanism? And they're never going to get an answer from mathematical physics, and they don't understand why. They say, you're giving all this math and all this gibberish about moving concepts and so on. I didn't understand anything of that. Could you explain it in layman's terms? And the answer is, you got to take a course at the university to, you know, master's degree, PhD, to understand how this universe works. In other words, what they're going to do is give you a bunch of math, and they still won't be able to explain it to you. As Einstein said, you know, if you can't explain it to a barmaid, well, you don't know it well enough. And Feynman himself said, if you can't explain it to a 10-year-old boy, you know, why the sky is blue, then you don't know it well enough either. Okay, we covered the first 2 decades of the Nobel Prizes, and that gives us an idea of how quantum mechanics really progressed. Because once you look at the Nobel Prizes, who were the people who got the Nobel Prizes and for what? It gives you an idea, you know, of how so-called science, really mathematical physics, and more specifically quantum mechanics, progressed. Okay, so that's where we're headed. Okay, first guy is someone who, because we're talking about the third decade right now, okay, the beginning of the third decade, 1921. First guy to receive a Nobel is the big man himself, Master Einstein. And the funny part, or the ironic part, is he did not receive it for anything related to relativity, or they say for his services to theoretical physics. You could include, you know, his stuff about relativity there. But they really give it to him for the photoelectric effect, which is what? A quantum issue, an issue of the subatomic world of light, you know, of electrons. It's got really nothing to do with the cosmic world, which is what Einstein is really famous for. Okay, and essentially what Einstein did was say, look, if you in fact, this was discovered by Heinrich Hertz already in the 19th century, but Einstein in 1905 presents an equation. That's what they get Nobel Prizes for equations. And he puts an equation saying, look, this is the relationship, and he can explain it with discrete packets, which Max Planck discovered, you know, 4 years, 5 years earlier. And now Einstein gets his prize 16 years later. He wrote his paper in 1905. He gets his Nobel in 1921 for that discovery, or explanation, or really description, mathematical description. What is it? You shine light on a polished metal surface, and what it does is get current to flow. if you accept that current is a flow of something. Okay, in this case, they say it's electrons that are flowing. Okay, and that's a big monster there because that invokes the planetary model that we have even to today. That's the only way they can explain it. All these little beads, the valence electrons flow from atom to atom. Okay, that's what they say is electricity, and that's essentially the notion that Einstein helped create together with Planck and other people. Okay, so he gets his Nobel, and it turns out the following year, 1922, okay, we have this gentleman. His name is Niels Bohr, and these two gentlemen are the fathers of modern mathematical physics. 1921, 1922, Einstein, Bohr, that's it. That's a summary. We have general relativity. He didn't get it for general relativity, but that's the creative general relativity, which is one of the branches of mathematical physics. And the other guy is Niels Bohr. He's the quantum guy of mathematical physics. And there you have it. There's your summary right there, 1921, 1922. So what did Niels Bohr discover? Well, together with another fellow known as Ernest Rutherford, a guy from New Zealand, they came up with this notion of the planetary atom. Until then, they had a different atom, the plum pudding atom of Thomson, and now they changed that, and there was a revolution in mathematical physics in this religion, and they said, no, look, your atom is wrong. It's not that we have this plum pudding with all these negative charges embedded in there. No, we've got something else. We got this planetary model, which you see up there, okay, upper right-hand corner, where the electron bead goes around in different energy levels, eventually known as orbitals, eventually changed to saying, well, it doesn't really orbit in a circle like the Earth. It just, you can find it somewhere in there. That's the new version, okay? But essentially, again, the problem with this atom is that you cannot explain why the bead doesn't fall to the nucleus if it's negative and the nucleus is positive, and vice versa, why it doesn't fly out spontaneously. So you cannot explain either of those phenomena. It's just, it is. You know, magic wand, it is so. Okay, that's my magic wand. So they just said it is so. That's it. Take it or leave it. You like it or not, we don't care. You know, that's it. You got to swallow it. And this is what is taught to every kid on Earth. Okay. This fellow, Ernest Rutherford, he did not get a Nobel for the atom. He got it in chemistry in 1908 for something totally, well, not totally different. He was still working over there at the Cavendish Laboratory, trying to figure out something about atoms. I'm not going to go over that, but the only important thing, and for which he should have maybe received another Nobel Prize, a second one in physics, is for his alleged discovery of the proton in 1919. Okay, so he was able to conduct an experiment together with two of his buddies, Marsden and Geiger, and they carried out this experiment in which they shot some rays at gold foil, and some of them bounced back, and from that he concluded that an atom is mostly empty space except for the nucleus, which is a proton, which is charged positively, which has the opposite charge of the electron, which had already been proven by previous individuals. So they have this electron bead, which is negative. We don't know what negative means or why it's negative. And the positive proton, we don't know why it's positive or what positive means in physical terms. It's just a mathematical label. That's all it is. And so we have positive, negative. Now we have a great world, because just like the magnets have positive and negative, we have positive and negative within the atom. Okay? And so he got a good pat in the back for that, but he did not share the Nobel Prize with Mr. Bohr, which he should have, you would think, because he was at least an important contributor to the planetary model of the atom. And discovering the proton, well, I mean, I think that would have deserved a Nobel Prize, right? I think, that's my opinion. Okay, who came next? Well, let's see what this guy got his Nobel Prize and how he contributed to this quantum notion that was developing since the beginning of the century. His name is Millikan, okay? And what did he do for the fatherland? Well, what he did, he measured something. Okay? So he took some measurements. He ran an experiment, which the experiment, by the way, is quite neat, very interesting. I love it. Doesn't have anything to do with physics. No, maybe with technology. I don't know. But nothing to do with physics, because he did not explain anything. He measured, and he measured the charge on the electron. What's the charge on the electron? What is that? 1.6 times 10 to the minus 19 coulombs. What's a coulomb? Well, it's a standard invented by man. Just like the kilogram is something invented by man. So if you can say, well, this is half a kilogram, whatever, you know, then you've discovered the weight of a potato. It's half a kilogram. Okay, and I measured, I weighed it, and it weighs half a kilogram. So is that science? Because that's what Millikan did. He was able to do a fancy experiment, no doubt about that, no criticism there. Doesn't have anything to do with physics. That's where the criticism is. And if he just measured and with his oil drop experiment measured the charge on the electron, what does that tell us about the nature of how Mother Nature runs her shop? What does it tell us about gravity? What does it tell us about magnetism? What does it tell us about electricity? I mean, the nature, the physical entities that mediate these phenomena. All he did was measure in terms of other standards that we created. If we take all these standards, we take them to another planet, and they are as developed as we are, they won't understand and say, oh, we have these other measurements. So all these laws change over there. The relations would be the same, but they would have different units, different measurements, etc. So what does that tell us? I mean, we've got numbers, we've got units, we still don't know what those numbers and units represent. Okay? So the fact that he measured so many coulombs does not tell me anything about what an electron is. Okay, is it a bead that goes around the atom, like Mr. Bohr said? That's the issue. Okay, that's where I'm headed with all this. This is where the criticism is. That we don't have, here we are 100 years later, we're still trying to figure out, what an atom is. We don't know what magnetism is. Nobody knows what gravity is. No one can explain it in rational terms. But they all get Nobels and they all say, oh, we know. Why do you know? Well, look at all the technology we developed. Technology does not tell us anything about the nature of how Mother Nature runs her shop or Father Universe runs his cosmos out there. Okay, and that's where the problem is. The problem is we have no real understanding. It's like I said the other day, they're making equations on turtles. They're experts on equations on turtles, and Mother Nature's running the show with eagles. And so their invisible turtles they say, we cannot explain anything with the turtles. But here are all the equations for turtles. And Mother Nature, Father Universe, do everything with eagles, or with birds or whatever. Okay, here's a couple of guys who immediately won a Nobel. Why? Because they confirmed the big boss of mathematical physics of those days, Mr. Bohr. He had grown to be a monster, right? He was the head honcho in physics together with Einstein until only Mr. Bohr remained, okay? And so what did these people do? Well, first of all, they discovered something. And the first question is discovery physics? Or is explanation physics? Again, if you bump into an elephant, you say, I'm the first person who discovered an elephant on planet Earth. Do you get a Nobel for that? Is that physics? Or is it thinking very hard on how the magician did his trick? How did he do that trick? That discovery, he burned some calories, but bumping into an elephant by mistake or accidentally, that's not physics. And so these guys discovered something. Okay, they did some experiment in the lab. They discovered what? They discovered a phenomenon. In other words, they discovered something that happened. And something that happened was the visible part. The invisible part is what they did not observe. They could not observe with their eyes the invisible stuff. All they could observe is the visible stuff. And based on that, they inferred, which they call proved, they inferred that what caused it were photons and electrons, electron beads. So that's an inference, but they put it out there as proof. We've proven, we know. This is where the danger comes in, when they prove. Okay? So what did these guys discover and prove? Okay, what they did was, said after the publication of Niels Bohr's theory, which was not a theory, by the way, on the structure of the atom, theory of the structure of the atom, that's not an explanation. That's known as a hypothesis. That's an assumption. Okay, you make an assumption of what the atom might look like, and then you create a theory which is explaining a phenomenon. These people are saying that describing the structure of an atom is a theory. That's where we fail already from the start. That's not a theory. Theory is always an explanation, not a description. Okay, that's the first issue. Okay, Gustav Hertz, by the way, he was the nephew of Heinrich Hertz, the guy who came up with the photoelectric effect, and the electromagnetic waves, the radio waves. And James Franck conducted an experiment in 1913 to verify it. To verify who? The big boss. I mean, if you verify the big boss, you prove him right, man, you're in line for a Nobel. Because the previous guy who won a Nobel, he recommends who the next guy should get it, should get a Nobel medal. Okay, that's how it works in that world. Okay, it's a buddy-buddy world. A potential difference was applied to a tube containing a low-pressure gas. Okay? When the potential difference was increased, the current flowing through the tube also increased until it reached a certain voltage when it suddenly declined. Okay? The results supported Niels Bohr's theory. Theory? Oh, what theory? In which electrons can only have specific discrete energies. That's not a theory. That's like a recommendation. That's not a theory. Okay? You have to explain why they can only have discrete energies, not say that they do, which is what Bohr did here. Bohr just said they do. I measured and I found through my experiments that they can only have discrete energies. Well, you haven't explained anything. You haven't explained why that's the case. Why does the little bead go back and forth? Why does a bead have this energy here and this other energy here? All he did was look at the spectrum of hydrogen, probably other elements as well, and figured out that, oh yeah, it's chopped off here, chopped off there. They can only have discrete energies, and just like the photon, the quantum, it can only have, packets, and the electron was more or less the same. So they say, oh, there, that proves that the electron is a little bead that jumps back and forth between what? Between energy levels. What's an energy level? Is that like a racetrack? I mean, a solid racetrack? What compels the electron to jump to that racetrack and then jump to the lower racetrack? Why does it stop there? Why doesn't it continue all the way to the center of the atom? Why does it fly out of the racetrack? Is there a fence there or something? The horse can't leave the racetrack? This is the issue. The issue, these people don't have an explanation. They only have descriptions. They call those theories, and these guys proved the so-called theory, the description of the atom, which, if they describe the turtle and Mother Nature does it with eagles, is worthless nonsense. Other equations. Because if they're describing a little bead and it's not a bead, then what have they described with their equations? Okay? You're describing a turtle and it turns out to be a snake, which is all around. Okay, which is more or less where we're headed. You'll see that in a couple more nobles. Okay, the potential difference increased the free electron's mobility until a certain energy level, whatever that is. We don't know what an energy level is. We don't know what energy is, but they talk about these things as if they knew what they're talking about. Again, racetracks. They jump to a higher energy orbit. Orbit? We went from Earth to Pluto and back. And we don't know why the asteroid goes from Earth orbit to Pluto orbit. Why does that do that? Why does it go outside the solar system? Thank God. I wish I knew, right? So yeah, you cannot explain any of this through beads. If the electron is a bead, you cannot explain it. Therefore, electron is not a bead, and all of what quantum proposes and has done for the last 100 years is not wrong. It's irrational, because you cannot explain anything with a quantum atom with an electron being a bead. So the electron has to be something other than a bead. Okay, I hope that message goes through, because if you cannot explain it with a bead after 100 years, you cannot just throw it in the towel and say, well, we'll never figure it out. And, Mother Nature or Father Universe doesn't think like us humans do, which is the answer that you get today. Well, I don't know if they think like you do, okay? But perhaps Father Universe and Mother Nature think in a different way from the mathematical physicists, okay? Physicists is a big name there. Mathematicians, that's all they are. Who got it next? Nobel Prize. Mr. Arthur Compton. And what did he come up with? He came up with a Compton effect. Whoa, what is that? Well, in all those days, remember the other day, they were dealing with X-rays. Well, so Mr. Compton went into the lab and he played around with X-rays because everybody was, it was the rage at the time. X-rays, oh, those, we can't see them, they're invisible, they're high frequency and they're waves. Waves? I thought quantum was about particles. And that's the problem here. That's the problem with Mr. Compton's so-called effect. Okay, the issue is you have incident X-rays. Okay, you point them at a metal surface. What is that? The photoelectric effect. Okay, so but now you're going to deal with X-rays. You point them at the metal surface, and it turns out a current runs one way and light goes the other way. Okay, so he measures the frequency of light and says, "Oh, I know what happened here. X-rays, high frequency. Okay, short wavelength, hits the metal surface. Some of the so-called energy, whatever energy is, hits the surface. It loses momentum, loses energy, loses whatever it loses. The electron goes in that direction because the little bead, came out of the atom and starts flowing in one direction. Those are that's electricity, the recoil electron there. And in the other direction, you get light. What is light? Well, you have a low frequency light, a longer wavelength. Okay, so he says, I know some of the energy or whatever that is went in the hitting, in the pushing out the electron. The other energy went into the light that came out, and obviously it's a lower energy, lower frequency, higher or longer wavelength. That's what he figured out. Okay, for that he got a Nobel. Okay, and what is interesting is that he's got the X-rays coming in, and what is that? Do you see a little particle there? No, it's a wave. Turns out X-rays are waves, and they knew that at the time. They knew it by the 1923. By the time he gets his Nobel, they already had confirmed and proved and etc. As we saw the other day, that X-rays were waves. Okay, in fact, it was proven in the second decade of the 20th century. Okay, so now we're in the third decade, and this guy says, okay, we know the X-rays come in, we know those are waves, and what comes out? Well, what comes out is also a wave. He measures the wave. But it turns out that Compton's effect is used by quantum mechanics to prove, to convince you that light can be presented or can be simulated in terms of particles, packets, chunks. We got a problem here, okay? Because what are we talking about? I mean, it turns out, his paper, in fact, you see just the picture there alone, let alone the equation. Oh, the equation at the top as well, see? It's all, that lambda there, that's wavelength. Now, how do you put particles in terms of wavelength? That's what I want you to tell me, okay? That's what you got to think about. Okay, so he says there, according to Einstein photoelectric effect theory, light consists of quantum packages, discrete chunks, right? And then he says Compton directed X-ray photons onto a metal surface in 1922, and electrons were emancipated. No. He just saw electricity, which he interpreted as being beads rolling from atom to atom, from valence band to valence band. Now they call that electricity. Okay, and that's an assumption. That's one explanation, but they cannot explain their atom, so forget about that explanation because they can't even point to their atom and say this is our atom. What are they using? They're using the planetary atom, which they, at the end of the presentation, they deny and reject. They say, no, that's not our atom, but that's the one we're going to explain electricity with. So we have to reject their atom, therefore their electricity goes down the drain. We don't know that electricity is a flow of electron beads from atom to atom, but this is what he's saying it is. But it turns out that he says, look, the X-ray photons onto a metal surface, electrons were emancipated, great. The X-rays wavelength. I thought we were talking about photons. I thought the Compton effect explains that or justifies or describes that light is what? Is made of packets of, discrete packets. So what is this wavelength? What is the wavelength of a packet? Okay, and yeah, they try to make the wave look like a packet so that you get the idea it's a packet. And that's why I always ask, does the wave packet that comes from the Andromeda galaxy, where does it start and where does it end? In other words, you got this little curlicue, like you see there. Does it stretch all the way from Andromeda to your eye? When you look at Andromeda, is that wavelength all the way to your eye? Or is it a little sailboat that has a beginning and an end that's traveling, during millions of years to reach your eye? I mean, are we talking about photons or are we talking something that stretches from here to there? That's what they needed to clarify. And today we don't have a clarification for that with the wave and particle models of quantum mechanics. Meaning that maybe we've got the wrong hypothesis. Maybe we got the wrong entity with which we're simulating light. Maybe it's time for a change. Okay, the rope. Rope is an elongated thing that stretches all the way from Andromeda to us. We can understand that. And it's undulated, it's straight, it's got all the features of light, and you cannot explain the same thing, and it's also round trip. So the Andromeda guy sees you and you see him, millions of years difference. But you can explain with a rope, but you cannot explain with something traveling all the way to Earth. Okay, so this is the issue. Anyways, he explained in terms of wavelength. What did he do? He didn't really explain it. He described it. Okay, it says there. Okay, the experiment confirmed, proved, they always confirm and prove that electromagnetic radiation could also be described as photon particles. And he did it with wavelengths, so you figure it out. This is the problem with what's going on in quantum mechanics. Okay, here's a picture of what this fellow did. That's the metal surface. Here you have the atoms, and you have your rolling beads. Okay, the electrons going around, and the little curlicue arrows there. Those are the energy that it releases and receives. Okay, because remember, Bohr's model says that you receive and you emit. The atom, right? The atom receives and emits energy, which is light. Okay, so that's what the curly cues there, the little arrows represent. Okay, now we're going to send some X-rays on this metal surface. Okay, stand by. There it is. You have the now we have the X-rays hitting the surface of the metal surface. Okay, and what happens from there is that you get what is called this Compton scattering. In the one direction, you get the electricity, which is on the upper right, and those are the electron beads. They're going from atom to atom. I didn't draw the atoms. And in the other direction, you see that the wavelength has become longer. Okay, and it's the same speed, but what changes is really the color, the wavelength, the frequency. So you see the incoming X-rays, high frequency, and what comes out is low frequency. Or if you wish to say it in different terms, you can say what comes in is short wavelength, and what comes in is short wavelength. What comes out is long wavelength. Okay. How do we explain it in the rational world of science? Okay, we start with this metal surface. What are they? We don't have the little planetary atoms. What we have is these balls, these balloons, and they are all merged or connected. Either they're merged or connected through the electromagnetic robe. I didn't draw those. Okay, and now we're going to shine some X-rays on it. What is the X-rays? It's light. What is light? It's ropes connected from atom to atom. So here we have the ropes, and they're connected to some atom, which is the source of the X-rays, and it's connected to the atom, and it's what triggers the atoms to oscillate or vibrate like that. Okay. So what comes out? Well, what comes out is not something that travels. What comes out is a torsion along two channels. In one direction, we have a torsion of merged electron shells, which is what electricity is. And in the other direction, you have torsions of the rope, which is what light is. So we have a different model for Compton's effect that has very little to do with electron beads flying around, nucleus or proton balls. Okay. So there is a different model to consider, okay, for you to consider. Have we proven it? Have we shoved it down your throat? No. We explained it so that you understand it, so that you have something to choose. Go home, sleep on it, think whatever you want. It doesn't matter to science. You have the explanation of a mechanism now that you can sink your teeth into, and it's up to you to compare and make draw your own conclusions. Okay, who was the next guy? Got the wrong guy here. Hold it. This fellow is quite famous. His name is DeBroglie, French guy, and he's going to turn the tables around on the particle guys, on the photon guys. He says, look, even the electron, matter, supposedly matter. We're not talking about energy now. We're not talking about photons. We're talking about matter. Electrons themselves, little beads. Okay, they are not pinpoint like a dot. They are extended around the atom like a wavelength. In fact, an integral wavelength, as you see there. It sounds like, as a minimum, he's describing a fence, maybe a hula hoop, a ring, something like that. Maybe a shell. Could it be it's a balloon? Cloud, as they call it? Nah, could be. Okay, anyways, he discovered the wave nature of electrons. In the beginning of the 20th century, quantum physics evolved from the idea that energy is conveyed in only certain fixed amounts. Yeah, okay, that's what Planck said. He didn't explain it. He just described it that way because that's what he assumed, that he was talking about beads, little packets of whatever, of energy, of photons. An early finding indicated that light can be regarded as both waves and particles. No. Only in mathematical physics can it be regarded as both. Mother Nature and Father Universe stand in opposition to that. They can only do it with waves, or they can do it with particles. They have to reject waves because what are waves? Just a bunch of vectors. Moving vectors, which is what all these people always put out there. It's so ridiculous because people look at that and say, oh yeah, I see what it is. It's a wave. No, what you're staring at is vectors, magnitude and direction, which is wrong also because magnitudes don't have directions. What you're staring at are number lines. Bunch of arrows represent number lines. These number lines are moving. It's very scary stuff. Never do that. And the number lines travel at 90 degrees to each other because you have the electric number lines and you have the magnetic number lines. And they're like at 90 degrees to each other. The number 5 is 90 degrees to the other number 5. The one that goes horizontal. It's very scary stuff. Again, Twilight Zone, you can imagine. This, you cannot. All right? And what did he do? Well, he described something. You see it there, the word describe. In 1924, Louis de Broglie introduced the idea that particles, such as electrons, could be described not only as particles, but also as waves. That was his contribution to the fatherland. For that, he got a Nobel. So do we know now what an electron is after today? Is it a particle? Is it a wave? Well, it's your guess. Because of that, today we have the super duper electron for all of you to see, okay? You saw it here first, okay? I want recognition for this, okay? Here it is. This is the notion of electrons today. Okay, we have these waves. This is the electron. By different people. Everybody has all these different ideas. One has it as like a galaxy. Another one has it like a spherical wave from a given point. I don't know how far that electron extends. And then at the lower right-hand corner, the one in blue there that's moving up and down more or less, that's the one that the Swedes filmed a couple years ago. They haven't got a Nobel yet for it. They might get one in the future. But they say they filmed an electron. They say that's what an electron looks like. And I'm saying, well, you know, I mean, these guys should really get a Nobel, because if they were able to film an electron going up and down or vibrating or whatever you see there, they were able to film that. The atom is a cinch. I mean, you can film one electron. Electron is what? 1/1800 part of the mass of an atom, and a very tiny portion of the entire volume of an atom. It's like saying, you know, you were able to film an asteroid. If you can film an asteroid, you can tell me what the solar system looks like, or what the sun looks like, or what the earth and the sun look like. I mean, if you can see this little bead, hey, a bigger thing should be a cinch. So I don't want them to film the electron anymore. I want them to film now the atom, the hydrogen atom, and draw it for me. I want to see what a hydrogen atom looks like. Does it look like a bead going around a bowling ball? And if you say no, then we got a problem with that electron. How did they film the electron and miss the atom? So we got problems with all these people. They've proven everything, but they can't draw an atom for me. This is the problem. I want to see an atom. I want to know what a hydrogen atom looks like. I want it. I want to see an atom. Just draw an atom for me. And if you put atom, like in images in Google, you'll all get the same thing. You'll get the orbiting bead. You'll get the planetary. We're still dealing with the Bohr Rutherford model, and they have to use that model, because otherwise they cannot explain electricity, ionization, quantum jump. They cannot explain any of that. So they don't use DeBroglie's model at all. He said, look, I've proven it. I got a Nobel. You know, it's this fence going around the atom. They say, yeah, great. Forget it. You know, they don't use that. Whenever they have to explain a phenomenon, they use the bead. And of course, at the end of the show, they say, well, by the way, that's not our atom, and we don't understand how this universe works either. And everybody thinks they do, because look at all the technology they were able to develop. They developed the atom bomb. They should know, right? So that's where we stand today. Okay, who's next on the roster? We have this fellow. They had to give it to some Indian fellow, because otherwise, you know, some other countries would have protested. They said, hey, you know, you're just giving it to all these Austrians, Germans, and British. It's just like you're all handing the medals to each other. And how about us over here, the Chinese, the Indians, the Russians? You know, we don't get medals. So they had to, you know, spread the bounty around a little bit. And so what did this guy get a Nobel for? Well, he says, when light meets particles that are smaller than light's wavelength. Wavelength. We're talking about waves, right? In fact, you see the pictures, they're all waves. Okay, the light spreads in different directions. Okay, we got that scattering. What do we got? You can say it's refracted, diffracted, reflected. Any of those will be fine. Okay, so you point them at some liquid and you get all these colors or all these different wavelengths. Okay, so what? You described it. We already knew that. Okay, now what have we learned here? This occurs, for example, when light packets photons. Photons. I thought you were talking about wavelengths. What do you mean photon? I thought photon is a packet. How do you reconcile the photon, the little bead, with something which is extended and has a wavelength and a frequency? And who knows? Frequency you could still talk about in terms of particles. You know, how many particles pass through a given point. Wavelength? I don't know. That's the problem. So in 1928, Raman discovered that a small portion of the scattered light acquires other wavelengths. Again, wavelength, than that of the original light. This is because some of the incoming photons, photons' energy can be transferred to a molecule, giving it a higher level of energy. Well, we already knew all this, Raman. Sorry, I don't know where you've been. Here, let me show you. Okay, we've already did it. In fact, Newton was one of the first guys to do it. He shone light through a prism. What Raman did, he replaced the prism with a liquid. Essentially, it produced the same effect. Okay, that's essentially what he did. And he cannot tell me if light is waves like you see in the upper left there, upper right you see particles, or whether it's the rope model, which is probably the most rational of those three because you cannot explain light with either waves or particles. Okay, not a single phenomenon. You cannot explain the slit experiment. You cannot explain polarization. You cannot explain anything with the models proposed by quantum mechanics. With a rope, we can explain it easily. You know, the rope obviously extends from atom to atom, and when it comes out, well, you have different colors, Y, and different link lengths. Okay, the links change. And that's because, you know, they're going at a different angle. So now we can explain that very easily. No problem. And so Raman did not discover the nature of light, and he's still fooling around, you know, again with particles and waves. And so far we made no progress with all the quantum whatevers that they came up with. Okay, who came next? Well, this guy's very important. Here's where quantum really takes off with some of these guys. Okay. And again, he was a very close pal of Niels Bohr. So guess what? You know, in fact, it is said that Bohr once made him cry, Heisenberg. And I think it was Heisenberg was the junior partner, so to speak. And I think he made him cry. He said, "Look, if you don't buzzer for me, I'm not going to give you your Nobel." Okay, he said, "Oh, please, Master Bohr, give me my Nobel. You know, I'll be a nobody otherwise." Okay. Okay, what did this guy do for the fatherland? Well, he said for the creation of quantum mechanics. Together with Niels Bohr, I guess you can say they are the two fathers, maybe Born and a couple others, Dirac, Chadwick. There's several, but I mean, these two guys, Bohr and Heisenberg, they're the originators and the guys who pushed for quantum mechanics and came up with the Copenhagen interpretation of quantum mechanics, which was the first one. Then they came up with other nonsense, bigger nonsense. I thought that was terrible, but what came after was even worse. You know, the many worlds and so on. You know, again, Twilight Zone, easy. Quantum mechanics, impossible. Okay, so 1925, Werner Heisenberg formulated a type of quantum mechanics based on matrices. Okay, sounds like math. Matrix? Unless he's talking about the movie, I don't know. Okay, anyways, 1927, he proposed the uncertainty relation. Well, the uncertainty principle, also known as the principle of indeterminacy. You can't determine anything, that's why, okay? Setting limits for how precisely the position and velocity of a particle can be simultaneously determined. Heisenberg is telling you when the ball stands still, it doesn't move, and when it moves, it doesn't stand still. And yeah, I cannot determine precisely, you know, that as you approach static, no motion, you know, you lose notion of how much of motion, of its momentum. And the more it moves, the less you can fix the location, you know, the position. Great. I mean, you know, I think he deserves a Nobel. Oh, he did get a Nobel. Oh, sorry. Yeah, he got a Nobel for that. Yeah, you wonder. Okay, who came next? Well, here we have a duo. Okay, they came together, but each one with a little different thing. But they had to split the metal in half and give half to each other, each of them. In 1926, Erwin Schrodinger formulated a wave equation that accurately described energy levels of electrons in atoms. Now, I don't like to trivialize what Schrodinger did because there's one positive aspect of Schrodinger's equation, and that's that it maps, listen to this, okay? It maps what an atom looks like, really looks like. All you have to do is replace the electron bead. Then you're okay. Then you're insanity, okay? You have to replace the electron bead and do more or less what Max Born did. And says, look, treat it like a cloud. I don't like the word cloud. I like the word balloon. I like the word membrane. I like the word shell. Those are better descriptions for what an electron is. An electron is a balloon, as you see all those balloons, which everybody who does quantum mechanics simulates with balloons. They tie balloons together and say, look, this is what this atom looks like, this is what this other atom looks like. How do they do it? With balloons. They call those energy levels, which is a mathematical concept. They call them orbitals, mathematical concept. We don't care about any of that. They're balloons. They're talking about membranes. Okay, that's what they're talking about. That's what they've been describing all these years. And so it says, so in that sense, Schrodinger's equation is good because it maps what an atom looks like. Okay, so this is what's good about Schrodinger's equation. Otherwise, Paul Dirac, what did he do for the fatherland? This guy, he should be removed from science completely. I mean, he provided nothing to science. Backwardness, maybe, you know. We went back into the Stone Age with this guy. 1928, Paul Dirac formulated. Sounds like math. Fully relativistic quantum theory. Relativistic quantum theory. Oh man, love that. I'm sure Einstein is rolling in his grave. theory, the equation. Huh? Quantum theory, the equation gave solutions. Theory is not an equation. A theory is not a bunch of solutions or calculations. That's not what a theory is. An equation can only describe. Science or a theory is not about describing. It's about explaining. Explain something. That's where you have to break your brain. But to measure something and say this is the equation, this is the equation of a chair. 4 legs, 1 backrest, a seat, and 2 armrests. So the equation is 4 + 1 + 1 + 2. Okay, we have the equation. What have you explained? How to sit? I mean, what is the point of that? So all these people are doing is describing something that they can't see, that they're assuming is mediated by particles. Every now and then they get the annoying wave in there, and they say, well, we'll use the transverse wave to explain this little piece of it, and then we'll get rid of it. We'll put it in our equation as wavelength, then we get rid of it, and then we'll continue dealing with the particle. That's how they're doing this. So you say, well, is light, is the electron an atom, a U, because they even say macro objects are waves. Is it a particle or a wave? And they say, it's both. But they don't say it that way. They trick you and they say, well, it behaves. It behaves here as a particle, and it behaves here as a wave. Wait, all you did is say in different words that it is a wave here, and it is a particle there. And hopefully Mother Nature and Father Universe don't go back and forth between particles and waves. But this is what these people are saying. And they're saying they represent that Mother Nature and Father Universe and God and the devil sent them to earth to represent them. I think they're going to be punished in hell up there, down there somewhere. Okay, so the equation gave solutions that he interpreted as being caused by a particle, equivalent to the electron, but with a positive charge. Yeah, what Dirac invented, his Dirac sea full of charges out there, whatever charges are, coulombs, 1.6 times 10 to the minus 19. Well, these were positive and these were negatives, and when you get those two equations together, you get 0. Oh my God. So yeah, you have the electron and the anti-electron, that's the positron. You put them together and you get kaboom, 0, zip. They turn into space, which is what? Made of particles. Space is made out of positive and negative charges that come together and they form space, nothing. Okay, great. So you have a black ball plus a white ball and you get a what? A no ball. That's what Mr. Dirac broke his head on. That's what he did for the fatherland. Who comes next in this? Well, here we have Mr. Chadwick. Okay, and what did he do for history, for science? Well, the discovery, he bumped into what? A neutron? Okay, so what does that mean? When Becker and both directed alpha particles, helium nuclei, okay, at beryllium in 1930, a strong penetrating radiation was emitted. One hypothesis was that this could be high energy electromagnetic radiation. Radiation, I thought that's a concept. Okay, so it can't be an it. That's like saying this is electromagnetic love. Okay, what's love? I mean, is that a physical object? So radiation is not a physical object, but they treat it as an object in all their writing, so you think they're saying, oh, it's radiation. Yeah, I know what they're talking about. May the force be with you kind of thing. That light comes out of there. It's the force, the radiation, the energy, the mass, whatever comes out of there, charge. Okay, one hypothesis was that this could be high energy electromagnetic radiation in 1932. However, James Chadwick proved, he convinced all his buddies, that it consisted of a neutral particle with about the same mass as a proton. Okay, so its existence now proven. Okay, it was called a neutron. So they proven, you can't, what does prove mean? It means you can't challenge it, because they're going to shove down your throat that it was proven, and you have no chance of contesting what they proved. Okay, and here we have the comparison. Well, you have the rope model of the neutron. Okay, and we show that it has not been proven by Mr. Chadwick. Okay, because what he said is a particle, and we're saying it's not a particle. It's a crossroads of ropes. So whereas the proton is a convergence of threads because it's surrounded by an electron membrane, a balloon. Okay, and so the only thing that continues to the center of the atom are threads, individual threads. In the case of the neutron, the reason it's neutral, it doesn't have so-called charge, it doesn't do quantum jumping, okay, and therefore it doesn't emit really light, okay, is that what? It's a crossroads of ropes. Somewhere the ropes from every atom in the universe have to crisscross. especially where there's lots of matter, like close to a solar system like ours. Then you have a bunch of matter there. And in that region, you're going to have lots of ropes crisscrossing. You're going to have lots of neutrons. Okay? You're going to have lots of neutrons because here you have an atom, but that's where the rope ends and continues on the other side of the atom. But somewhere there are crisscrossing of ropes, and that's what we call the neutron. Okay? And there's so many gazillions of atoms in our region of the solar system, in this region of this bundle of matter we have here, that, yeah, all those forms what we call neutrons. So we have a different model for the same thing that Mr. Chadwick proved to his colleagues. Okay, here we have a fellow we talked about the other day, Mr. Carl Anderson, and he invented the suppositron. Why? Because he made a supposition. Okay, and he said for his discovery of the positron. Yeah, why is it suppositron? Because he assumed, okay, that he was looking at a trace. Never occurred to him that maybe it's a rope that banged against his little plate there. Okay, we have all these ropes just spinning around. Actually, not rope. It's a thread. So that's my mistake there. No, it's a thread, and you have all these gazillions of threads going around, which we call magnetism. Okay, and these threads just goes right through, and made a mark. It's like whipping the paint on the wall with a whip. That's different than running a ball across the paint on the wall. Two different mechanisms. Doesn't mean you have to believe one or the other. I'm just giving you an alternative to say, well, is it balls? Is it discrete balls? Because with discrete balls, they cannot explain anything. They admit it. So maybe it's time to look at alternatives. So this is the problem with the suppositron that Carl Anderson proved to all his colleagues. Okay, and for what he got his Nobel. Maybe he's got to return his Nobel from hell. I don't know. Okay, here's the next fellow, Enrico Fermi. Very important guy because he also worked on the bomb. Okay, for the U.S. government. What did he do? He demonstrated something. Okay. New radioactive elements and discovery of nuclear reaction. So is demonstrating something, maybe through an experiment, or discovering something, does that constitute physics? Is that what physics is about? Or is physics about explaining? Again, this is the issue. This is the issue before you. Tell me what physics is about. What is science about? Is it about describing? Is that what a theory is? Next fellow, let's see what he did for the fatherland. Development of a method and his discovery of something, of a magnetic moment of the proton. So is developing a method, is that physics? Is discovery of something, whatever, maybe bumping against the wall. I discovered the wall. Is that science? Yeah, I discovered the wall. I'm the first guy who discovered this wall. Okay, so you get a Nobel for that. Again, we're talking about what is physics, what is science. Is this what physics is about? These guys are just giving Nobels to each other for discovering stuff that they're just making assumptions about the underlying entities that mediate these phenomena. And they say, I discovered a new effect, a new behavior. And here's the mathematical description. Give me my Nobel. That's what they're saying. That's what they're doing. And even to this day. Okay, a couple more guys here with Nobels. So we finish up with the Nobel guys here in quantum mechanics. Some of the fellows that in between I missed or I did not include here because they did not relate directly to quantum mechanics. Okay, so I'm only including people here today that are related to quantum mechanics. For his resonance method. So I tell you a method how to make a shoe, and that's science. That's physics. So you got to cut here, the letter, and sew it here. That's the method. That's the specification. That's the recommendation. Is that what science is about? Creating methods. So whatever he did, and again, he did a magnetic field. He's still talking about magnetic field. He doesn't know what a magnetic field is. All he did is invent a method on something he's assuming, working in the dark. Then he said, we don't understand it, but here's the method. Okay, another important fellow that comes up here, more important than this previous guy. His name is Wolfgang Pauli. Okay, again, what did he invent? He invented the exclusion principle. And you say, what the hell is that? Well, in a nutshell, okay, we have one electron here in an atom, another electron on the other side. This one spins clockwise, the other one spins counterclockwise. So he says you can't have, among other things, but it's more involved, but I'm just synthesizing here. You can't have two electrons in the same orbital in the same region, okay, both turning in the same direction, both having the same spins. One has to go clockwise, the other one has to, he doesn't say clockwise and counterclockwise because they don't know even what spin is. If the spin is not a top, that you spin. They use the word spin. You think they're talking about a top, and when you put them against the wall and say, what do you exactly mean by spin? And it's more like an orientation, like a mark. Like you put a mark on the top, okay? You spin it, you let it fall, and when it falls, you say, okay, the mark is pointing upwards, I'll call that spin 1. Oh, it's pointing downwards, I'll call that spin -1. To the sides, half, minus half, whatever. So this is what they did. So spin is not spin. That's the first issue. But he's saying that one has the opposite spin of the other, whatever spin is. Under the rope model, very easy. If it's a membrane, and that membrane everywhere around, like DeBroglie said, is like, this integral wave going around because it's wavy, that it's a membrane that is wavy. Well, here, if it's turning like this, let's see if I get rid of this so that you can see what I'm saying here. Imagine this, okay? They're going like this on both sides, or going inwards. Well, no matter how you do it, it's going to be one opposite the other. The spin is going to be different on one side of the membrane as it is on the other. We're done. Kindergarten stuff, okay? As long as you do physics, you don't break your brain. It's when you try to do it mathematically and talk about spin, when you don't know what spin is, you don't even define it because you have no idea. Then you say, well, for some reason I have to invent this principle. The, what is it? The, not indeterminacy, look it up again. The exclusion principle. So you invent this exclusion principle or the complementarity principle, meaning that a particle, that light can be both a wave and a particle, or the uncertainty principle, or the principle of equivalence. They invent all these principles because they don't know what the hell they're talking about. So they have to invent these laws, these principles, these underlying cornerstones, foundations. So you say, hey, you can't break the principle because that's just a principle. And they're all nonsensical principles because they don't understand the foundation of that principle. They just say, we observe, this is what we see, and this is the principle we're going to put as our foundation. But they don't understand the why, the cause, the mechanism. That's why they have to invent these principles. But if you say, well, again, the membrane, then the exclusion principle is easy. Here it goes clockwise, here it goes counterclockwise. And if you go in the other direction, same thing. One side of the membrane has to go. Look up. I should have put that up here, but look up a torus. The spinning torus. And tell me what's one side of the torus, what does it look like with respect to the other? It's turning inwards, One side is clockwise, the other one is counterclockwise, or vice versa. Very simple stuff. That's physics. Not what the nonsense that mathematical physicists do. Okay, do I have any more of these guys? No, that was the end of it. I think he was the last guy. And so here are the conclusions, or for you to ponder, which is where I started the other day. Here I end here with this same corollary or conclusion. Is physics about inventing, discovering, measuring, coming up with an equation, describing something, whether qualitatively or quantitatively? Is it about winning prizes? Okay. Are we doing physics? Is that what these people are doing? Well, we are. We don't know what they're doing, but they give Nobel Prizes and make a lot of money talking about this new religion, the one that replaced the old traditional religions, because now they have knowledge. How did they prove it? With equations and technology, which has nothing to do with explanations, which is what science is about.